There is also a land surface scheme known as joules in the model. And this land surface scheme represents dynamic vegetation such as trees, grasses and shrubs, plus inland water and urban regions. And this is very important for heat, energy and water balances between the atmosphere and the land surface. So what I've described so far is essentially all of the science which is included in the UK Earth System model, so the parent model of the New Zealand Earth System model. We also do have two more things in our model which are unique, and one of them is an improvement to stratospheric chemistry scheme. This is something which New Zealand has a lot of expertise in, and so this is something that we've added to the Earth System model framework. Essentially, what happens in the addition that we've made is that the solar cycle, which varies over time, as the images on the left-hand side show, and this solar cycle dependence of ozone chemistry, known as photolysis, is something that we've included in the model ourselves. So this is present in the New Zealand Earth System model. And if we look at making the South Pacific the center of the world, just taking this map from the New Zealand Herald, I thought it was quite nice. It puts New Zealand and the South Pacific right in the center of things for a change. What we do in our model is we have an embedded high-resolution ocean model in the New Zealand and South Pacific region. And this work was mainly coded up and put into the model by Erik, who'll be talking later. And the animated GIF on the bottom right-hand side shows the difference between the underlying background global 1 degree model, and in the upper panel shows the resolution of the embedded NZESM high-resolution ocean model. Now, because with climate and Earth system models, I mean, we don't know exactly what the future will hold in terms of greenhouse gas emissions and so forth. And so what we've done is we've done various different simulations for the historical period from leading up to 2015, which is the end of the so-called historical period in the IPCC definition. And then we've run the model forward for 3 different future emissions pathways out to 2100. And so what we've done is we've done essentially at high, medium and low resolutions from 2015 out to 2100. And we've done ensembles of these simulations, which means we've run each of them more than once to get an idea of the statistical dispersion within the ensembles themselves. So these future pathways are often called SSPs, or shared socioeconomic pathways, and they reflect possible future scenarios of greenhouse gas emissions and land use. They're broadly comparable with RCPs, which some people still refer to, which are representative concentration pathways used in previous reports from the IPCC. And on the panel on the right-hand side, I've just circled the SSP 1, 2, and 3 scenarios that we have run here in New Zealand. There are quite a few more of these SSPs in existence, and some modeling centers around the world have done ensembles of simulations for all of them. However, as a relatively small partner in the IPCC process, we have only run 3 simulations, and the NZESM simulations we've run have actually, they're not actually part of the IPCC database, which people can log on to online and download the data directly from. However, the data is available for stakeholders and collaborators to use already. That data is already around and is being used as we speak. So just to put this in a bit more detail, this is a graph here just showing an example variable, which is a global precipitation amount. And what this is just showing is that we have done 4 historical hindcast simulations, starting from different dates from 1950, 1940, and 1850. And we've done these high emissions, medium emissions, and low emissions future ensemble runs out to 2100. And this is just, I don't want you to read too much specifically into the specific data that I'm showing here. However, the point is that we have global data for the 4 hindcasts and 3 ensembles of 3 members out to 2100. So we have an awful lot of data which we are examining at the moment and will be examining for a while to come due to the volume of it. And we can look at data from around the world because it is a global model, but we can also zoom in on the oceanic processes in our region using the high resolution ocean model. And just as I've just got a few brief examples of the type of data which we're looking at the moment. What I've got here is some figures showing in the top left the sea surface temperature. Actually, sorry, no, it's the surface air temperature. Sorry, of the model, the NZESM. On the right hand side, the blue region, the rectangle, shows the region where a high resolution ocean model is embedded, and the background colors and contours show the changes to the surface air temperature. And one of the interesting things here is that there are certain regions of the model which of the area, sorry, which show an increase in temperature and certain areas which show a decrease. And overall, if you examine the bottom 2 graphs here, which show the temperature response with respect to observations, overall in the region immediately surrounding New Zealand, the agreement between observations and simulation and observations, sorry, is improved. And this is something which a paper has already been published on this, led by Erik Behrens. This is already in the published domain. One of the things which I personally look at, as opposed to the specifics of the ocean response, is looking at the atmospheric response. And so what I've plotted up here is the response of the total cloud amount with the new ocean model. And if you compare if I just go back one slide, you can see that broadly speaking, where we have a decrease in temperature, we have an increase in cloud. And one thing which I've been researching specifically over the last couple of months is the effect on different parts of the cloud spectrum. So what's often done in cloud physics studies is we split the clouds into 9 dominant types, for example, stratocumulus in the bottom center panel, and see how that is affected by changing the underlying ocean model. What we found is that by including a high resolution nested ocean, we actually see a substantial change to low cloud, which is stratocumulus, but is also it's a very common cloud type, and it's also not too thick and not too thin. So it's very much a kind of bellwether cloud type for global responses. And what we found is this leads to a significantly better agreement between the models and observations over the Southern Ocean when we consider shortwave radiation budget. And the radiation budget is a large area of study globally in climate science. And I've circled here the area of the Kevin Trenberth's famous radiation figure, and I've circled the area which our model has substantially improved in our simulations. This work is being written up at the moment and hopefully will be published before not too long. And also, just briefly, another area which the HPC and supercomputer has enabled us to look at in more detail than before is storm analyses and climatologies of storms over the South Pacific and New Zealand region. One example, just one particular example of one particular storm that I've looked at is storm Giselle from 1968, which caused extensive damage across New Zealand. The point is that using a piece of open source storm tracking software, we're able to track low and high pressure systems globally and zoom in on the New Zealand region. And the point of the figure on the right is just to show that the when you feed in a field of sea level pressure to the storm tracking software, it accurately tracks the real life storm track of Storm Giselle. And just an example picture here of the type of output that we can look at, although it's very flexible. The colored circles show the surface sea level pressure of the origin of a particular storm, and the black lines show the storm tracks themselves as they go through time and slowly die out as they reach generally colder waters. And so, although the NZESM can't be used for prediction of individual systems, we can use our data to better understand how storm occurrence may change in the future. And this is something which I'm working on as we speak, and I'm excited to start talking about this in more detail and publish this in the future. This particular figure shows simulated storm systems that hit, in inverted commas, Aotearoa and New Zealand in a particular time period. So that's about it from me. So what I'm going to do now is just briefly thank the Deep South National Science Challenge, who funded this work, my colleagues Olaf, Erik, Vidya, Guang, Zeng, and many other people from across the Met Office Unified Model Partnership, and to you for your attention. And so now I'd just like to pass over to Erik.
All right, thank you, Jonny. I hope you guys can hear me. I try to share my screen. All right, so I hope you can see my presentation.
Yes, Erik, we can hear you and we can see your presentation. Thanks.
Perfect. Okay. Thanks, Jonny, for the first part of this presentation and good introduction into New Zealand's Earth system model. So in the second part of this presentation, so my part, I will mainly focus on the oceanic results of the Earth system model. So, in particular, I will talk a bit more about ongoing work which we do around evaluating how the Earth system model is able to predict and simulate marine heat waves in our region around New Zealand or the Southwest Pacific. But before I come to this part of my presentation, I briefly like to mention that we have undertaken quite a bit of evaluation of the NZESM already to sort of highlight what we actually gain by having this high resolution ocean model embedded around New Zealand, which improves ocean circulation, ocean currents, and what are the implications are. So what is the benefit which we actually gain out of the system? So we were looking at questions like, what are the impacts on ocean currents and their variability? How have model biases in the existing model have been changed? And what are the downstream processes or downstream effects of those changes? And as Jonny was saying, so most of that is already written up and freely accessible in a journal publication, which is shown here. So the main bottom line from this publication is sort of that a few of the main biases which we've seen in the parent model, which is the UKSM, have been reduced in the nested region. So that is one of the main achievements, which I think, and the other one, which has been quite beneficial, at least from my point of view, is the just being able to have a lot of more spatial resolution, which allows that you are able to zoom into some regions and look how certain areas change over time, which we wouldn't have been not be able to do based on the coarse parent model which we had so far. But with that, I would just now jump to the main part of my presentation, which is focusing on marine heatwave projections in the New Zealand Earth system model. So Jonny was already describing what kind of simulations we have available in NZESM. So the schematic on the right, you can see my pointer. I hope so. So we have a historical simulation available, and then we have those three future scenarios available, depending, so they differ in the amount of CO2 which are being emitted. So it's just a schematic, so it's not a, just to illustrate. So low emission scenario, middle of the road scenario, and high emission scenario. And in each of those simulations, we have three ensemble members available, which allows us to dig a bit further into the nitty-gritty of model uncertainties. So what we tried to do in this project around mare and heat waves is to evaluate how NZESM is actually able to capture mare and heat waves. So in terms of where and when do mare and heat waves occur. And then, of course, we are interested in how does the NZESM thinks or project changes, how the NZESM thinks that mare and heat waves are going to change in the future. And then, because we have those three different simulations available, ensemble members, we then can also ask the question around how robust are actually those future projections. Just a brief recap for people who are not working with mare and heat waves all the time. So mare and heat wave is a metric which is based on sea surface temperatures or sea surface temperature anomalies compared to long-term climatology. And this schematic sort of illustrates the concept behind it. So a climatology, or the 50 percentile climatology at a given point, is shown here by the blue line over time. So can be anything, and then the 90th percentile by the orange line. And then you have your observed or model time series, which is illustrated here by the black line. And if the SST anomaly exceeds the 90th percentile climatology for more than 5 consecutive days, that is when we call this period a mare and heat wave. And then you can calculate all kind of metrics from that. So what is the intensity of this mare and heat wave, which is simply the difference of the temperature compared to the baseline, and then also the length of the mare and heat wave. And that is what I'm going to show in the following slides. So we are now looking at mare and heat wave intensities. This is still a bit work in progress, but hopefully we get this soon also in the review process. So the top panel shows mare and heat wave intensity from the Earth system model ensemble over the past or last 20 years of the historical simulation, so from 1995 to 2014, in comparison to observations, which is the middle panel here, and then the difference between both, which is sort of the model bias, is shown in the bottom. And then it turns out at over the historical period, or at least the NZESM overestimates mare and heat wave intensities of around 1 degree compared to observations. But in general, it gets the pattern right. So that means that the subtropical waters experience more intense heat waves than subantarctic waters. And then, because we now have those different SSPs available, where the different pathways, we can now look how those mare and heat wave characteristics change over time. And we decided to have 2 time slices, so sort of middle of the century from 2040 to 2059, and then the last 20 years of the future projection, and simply compare it to the present day historical 20 years. And we see and we can do the same, of course, for the other SSPs here as well, 4.5 and 7.0 at the bottom row. And so overall, there is a lot of regional pattern emerging, but in general, we see that in SSP 2.6 on average, and heat waves around become roughly 1.5 degrees, in SSP 4.5, 1 degree, and in SSP 7.5, 1.5 degree warmer than present day conditions by 2100. All right, and then another metric which we also try to calculate is annual Mean heatwave days. That is simply the number of how many days per year Mean heatwave conditions are being met at a certain location. And that the top panel shows again this metric for the NZESM example. Again, last 20 years of the historical simulation in comparison to the observations. And in this case, it turns out NZESM sort of underestimates the Mean heatwave days by around 10 days in subtropical waters, and there are few regions in the subantarctic waters where NZESM overestimates the annual Mean heatwave days. And then again, we compare that those future simulations compared to the historical simulation and see how those patterns change over time and depending on the scenario. Again, there's a lot of spatial variability and differences present, but overall we see that in SSP 2.6 on average, annual Mean heatwave days increase by more than 40 days, in SSP 4.5 more than 100 days, and more than 140 days for SSP 7.0, again compared to present day conditions. And then last but not least, I just wanted also to highlight again, because we have the high resolution ocean data now available, we can dig a bit further into some regional changes. So we defined a few regions which are quite important for a few, for fisheries, for example, aquaculture. So it was the Tasman Sea, the coastal waters around Tasmania, coastal waters around North and South Island of New Zealand, and just investigated how, for example, Mean heatwave intensity changes for those 3 locations. So, and just wanted to show the example here. So the blue shading here shows the observations, and the blue distribution, the green distribution is the NZESM example for the historical period. So in general, there is a bit of model bias towards those higher intensities, but in general, sort of the mean intensity fits quite nicely. And then we can look for the different SSPs, which are shown here, how this distribution actually changes over time. And then, so it really allows to see how those distribution changes, and that gives you a better understanding of what kind of Mean heat waves or temperature anomalies you actually like to experience by 2100. And with that, I would like to stop my presentation or sort of summarize what I talked about. So in general, in terms of Mean heat waves, NZESM overestimates intensities of Mean heat waves and underestimates annual Mean heat wave days so far for the historical period. And then in terms of future projections, Mean heat waves will become more frequent and more intense in the future, and the magnitude is highly controlled by what kind of pathway we decide to pursue. But in general, it appears that subtropical waters will show a larger warming signal, that subantarctic waters, this region in subtropics, will experience more intense heat waves than subantarctic waters. And some changes are also seen in the region of the subtropical front. That is simply because of changes in the location of the subtropical front, so the expanding of the subtropical gyres. And a few more things we have to think about is also that some of those regions which will experience from time to time also Mean heat wave conditions year-round. And with that, I would like to thank everyone for listening, and there might be time for a few questions.
Thank you very much, Erik. Thank you very much, Jonny. we have a couple of questions that came through the chat box. Please do use chat box for your questions, and thank you very much, Herb, for clarifying the acronyms. I'll start with Elodie's question. It says, good afternoon, and thank you for this presentation. As I understand, permafrost has starting to melt down without really knowing the consequences, impacts of methane being released. Was this taken in account in the simulations? And are we capable of predicting more about the meltdown? Thank you. Jonny or Erik?
I can take that question. So sure. So within the land surface model that is used, JULES, so the land environment simulator, there are representations of soil processes, hydrological processes, and how they interact with the atmosphere. So for example, as you were saying, for example, with permafrost, so methane exchanges with the atmosphere and knock-on effects on the carbon cycle. One thing which is worth saying though is because the model itself is global in nature, it is relatively low resolution, so of the order 100 kilometers or so in the horizontal. And also the soil scheme itself uses, I believe it's 5 vertical levels. And so although the processes which you and I would refer to as quote unquote permafrost, the resolution of the model is not as high enough to really give us an idea about regional aspects of local kind of cryogenic terrestrial climate interactions. So in summary, the processes that we are most interested in are those around the New Zealand region. But if people are interested in using the global data that we have to look at the effects on permafrost melt on atmospheric climate, that is something that we can get some useful information from the model, yes.
Thank you very much, Jonny. The next question is from Herb. Herb says, good afternoon, and many thanks for the presentation. 2 questions, please. One, what is the open source TC tracking software, and TC stands for tropical cyclone tracking software, that you're using? And 2, is there a plan for NIWA to use the HR, which is high resolution model, to provide local climate change projection for countries within the model domain? Thank you.
So firstly, the tracking software is it's a piece of software put on GitHub by Eric Oliver, who's a Canadian climate scientist, and I have pretty much used that code out of the box, so to speak. I made 1 or 2 very minor changes so that the version of the Python programming language that I use here was compatible. But that if you just Google for Eric Oliver storm tracking on GitHub, you'll find that. It's there, and I think it's been there for a couple of years. Although, as far as I'm aware, it's not been properly documented as yet. It is based on a previously documented ocean eddy tracking code. Anyway, so the next part 2, is there a plan for NIWA to use the high resolution model? So yes, so the one thing which we didn't talk about here is the fact that the global model data for the atmosphere is being downscaled for a region surrounding New Zealand by colleagues of ours here in NIWA in a separate project, which is the high resolution atmosphere modeling project. I'm not sure off the top of my head of the exact region which they are looking at, but I'm pretty sure it is New Zealand specific as opposed to kind of the South Pacific region. And so what I could do, if you're interested, is that I could pass your question on or to the regional climate modelers, colleagues of mine, who would be better able to answer that question.
Yeah, maybe I can just chip in. The regional model that we're using at the moment has a domain which is smaller than the high resolution ocean domain. So it's fully within that high resolution ocean domain, covering that at 12 kilometers. But we may switch regional model to something that has a stretched global grid, so it won't have a strict domain boundary anymore. Yeah, but the regional modeling that we do would always focus on the New Zealand region. Yeah, within the financial confines that we have at the moment. If in the future, somebody wants us to do high resolution modeling for the Pacific region, we could probably do that.
Okay, thank you. Next question is from Hendrik. The question is, have you considered to use the GNSS, which is Global Navigation Satellite System technology, for your Earth system models, using the GNSS frequencies to measure effect on the atmosphere? Thank you.
So to be honest, that's really not something I'm familiar with at all. I'm very happy for anyone else to jump in if they know any more about that. Those things are not currently used in the model, and it's not something I can really add much to, unfortunately. But if anyone else can, then do jump in.
Excellent. Now we open floor for questions. Any questions from the floor? And if I may, I'll cast the first one. This might be quite, the answer to this question might be quite obvious, but how important was high performance computing or supercomputer or scientific computer that you have in the process of using or utilizing this model?
I'll just jump in first, if that's okay. Yeah, I mean, the HPC, high performance computing capability is completely essential to this work. It's just something which you, as a modeling center or as a research group, it's something which you just simply can't do due to the CPU and memory requirements for these models. I mean, climate models and Earth system models are some of, if not the most complex pieces of software that exist in the world. And before we had the upgrade of the supercomputing system in New Zealand a few years ago, we wouldn't have been able to do these simulations at all. They just simply weren't powerful enough. So as you mentioned, it is quite simple. Without the HPC, we just couldn't do it.
Are you able to give us an idea on how long one simulation lasts for?
Yeah, so I mean, the simulations themselves do, it depends on the number of computing processes which you tell the computer to solve the equations, for example. But for the configurations that we've used, for example, a future scenario simulation running from 2015 out to 2100 would take something of the order of a month to maybe 5 weeks to run. So because we are simulating all of these different Earth system model processes at resolutions and at different resolutions for different parts of the model, and the amount of data which is output is huge. Of something of the order of 50 terabytes of data is produced for each simulation, and so, but the combination of all of those factors does mean that it does take a long time to run. So we'd love to do very large ensembles of 100 or more members, but it's just simply not computationally possible.
When you say 5 weeks, 1 month to 5 weeks, how many processes would you use in that, or how many CPU hours, or I mean, what would be the measures that could get us a bit better idea on how complex this calculation was? Yeah,
so in terms of so the number of CPUs used for a particular simulation is about 1,200 in the setup that we've used. I'd have to go and do the sums off to find out the precise number of CPU hours for a particular simulation, but it's the runs take somewhere of the order of a month or slightly longer and use about 1,200 CPUs.
Thank you. That's enough. So if we were to do something similar for Vanuatu or for some other member country, we would probably need the same resource to be available to us.
So the modeling framework itself is global in nature. So the model that Erik and I run, it doesn't have the capability of just running for a particular region. That's where the high resolution atmosphere models, for example, which come into their own, where you can specifically look at one particular area.
Excellent. Thank you very much. Another comment on chat is, let's just say that a couple of years ago, Jonny was by far our biggest user of compute time, very impressive usage, and we were happy to help with that. Thank you, Jeff, for that. Anyone else from the floor with a question or two? Otherwise, I'll have another one. Okay. Ferretti, did you want to? No? I saw your microphone clicking. No? Okay, so my next question is, you mentioned that you have a lot of data that you produced over time. How open are you to data sharing with regional organizations like SPC?
So at the moment, because the data itself is relatively newly available, we are starting now to work with colleagues and stakeholders to give access to this data. So we've been working with a company here in New Zealand, collaborating with them, and they've asked us to provide them with various bits of data to feed into their high resolution regional ocean model for their work. But my understanding is that the data is available for for collaborators and stakeholders and colleagues to use, but it's not a case of just kind of giving it out. It's not publicly available. So it's not like some climate model databases which are freely available to anyone in the world to look at. But if anyone is interested in using any of the data that we've talked about today, I'd encourage them to get in touch with us, and we can talk about how to make that data available.
Excellent. Thank you very much for that. It's an important outcome of this event. We now know that data can be shared, and NIWA is open for collaboration, and is looking forward to hear from us if we need any of the data that they might have available. Okay, Dean is asking, thank you for the presentation and sharing your impressive works. Are there plans for a future published set of model runs and their projections as a set of information resources that the Pacific region could use to inform actions and policy for adaptation and resilience planning, along with other sets of literature and tools available on future climate change projections and predictions, works in the Pacific region? Potential users of the information from the showcased work would add value for science and policy users in the Pacific. Jonny, would you be able to answer that one?
So with the different policy, the SSP's socioeconomic pathways that we've looked at so far, we have concentrated on these what we've generally termed low, middle, and high emissions pathways for the future. We are interested in possibility in the future of looking at some more SSPs. So two particular pathways of interest which we haven't looked at yet are essentially the extremes of the future emissions pathways, which would be heavy mitigation. For example, looking at trying to achieve Paris Accord 1.5 degree future climate change target, and the other extreme of that would be looking at a kind of what is often called a worst case scenario, where the it's a somewhat unrealistic scenario where essentially all of the fossil fuels available in the world are burnt and put into the atmosphere. However, some policymakers all around the world do often ask climate scientists for a worst case scenario. And so it comes down essentially to resource as to whether we can run those simulations and process the data to make it available. In terms of how that can specifically impact Pacific Island nations and the resolution of the global Earth system model itself is not high resolution enough to really give small island nation specific data if you compare different parts of the South Pacific. However, the data and resolution that we can achieve is certainly applicable to to commonalities of the South Pacific community. I hope that helps, but if that's not clear, then do get in touch with me and we can try and answer that better for you.
Thank you, Jonny. Another question is from Andrew. The question is, can you tell us who is the company doing high resolution modeling for the Pacific?
I guess so. Olaf is. I mean, I'm assuming it's not a secret.
Yeah.
So yeah, the company is Metocean Solutions, I think is the name. In terms of the involvement that we've had with them so far was around kind of contractual obligations as how the data is used and shared and that kind of thing. And so that's I'm not 100% sure what they will be specifically doing with the data and where they'll be publishing it or pushing it out there, but like I said, it's important to, and as Alex mentioned as well, it's important to emphasize that this data is there and is processed and archived and ready for colleagues and stakeholders to use it.
Thank you very much. We are out of time. It's 2:01, unless there is a burning question from the floor. No, I'd like to close this session and to thank and a big thank you to the guests from MFAT, DFAT, SPREP, and NIWA, of course, for presenting this magnificent work, and many thanks to our colleagues from SPC for joining us today. Thank you very much for your time, and looking forward to see you again next week when we will be presenting PICOS as a new SPC MFAT funded initiative. Thank you very much and have a good day. Bye.
Thank you.
Thank you.